So hello everyone, welcome back to this class. So in this class we will study directional stability and directional control. In last class we have done with lateral stability and lateral control. So already we have seen the stability and control about the two axes, right? Pitch and roll, right? And now in this class we will see about the z axis. Yeah, okay. So this is a positive yaw. Okay. So if the aircraft is disturbed, then it will build the side slip beta. This force has some distance with CG, so that will provide the yawing moment also. So it will try to kill the side slip like this. Okay. If for example, if the beta relativity is coming from this direction, the aircraft will try to enter into that condition. Okay. So that means if you increase beta, your turn will also increase, right? Yeah. Okay. So from this, what will be the Cn beta value? Positive or negative? Positive. Perfect. Because from the where the beta is coming, you are entering in that direction only. It's also called weathercock stability. Okay. Now, how it is coming? Already I told. The vertical force is coming. This has some distance with the CG, because this in last class we have seen that, right? This force into vertical distance, right? But now we are talking about yaw, right? So we'll take this distance, right? For example, like this is a vertical force. This is a aircraft fuselage reference line, for example, let's say, and your CG is, let's say, somewhere here. Okay. Your vertical tail is this. Okay. So now this vertical force into this distance, right? So I can write this distance as a LV. If you put the aircraft, your vertical force is this, right? This is the vertical force, right? That will try to rotate the aircraft in a positive yaw direction, right? So I can write yawing moment N equal to that lift force into this distance LV. Okay. Now you may write half rho V square S into B Cn, and this you can write half rho V square S V. Okay. Cl alpha of the vertical tail, and this beta plus sigma. Why? Beta is a side slip angle, and due to vertices there will be sideways angle, so total angle will be like a beta plus sigma, like we have seen in the downwash case, right? So in longitude there was a downwash, but here it is a sidewash. Okay. So beta plus sigma. Okay. Now, okay. Now you may write this question: half rho v square, this is Vt square, right? Vertical tail, eta V SV by S Cl alpha into beta plus sigma. Okay. Please correct me if I am wrong. SV by S B and LV LV, okay. Side wash angle, sigma is a side wash angle, like longitudinal case we have seen downwards, right? So you differentiate with respect to beta, what you will get? Eta V, SV, LV, SB 1 plus dou sigma by dou beta, okay. This value you can find out from the literature, dou sigma by dou beta. I have already given you the reference in the early class when I have given you the introduction to aircraft design lecture, okay. So Cn beta equal to eta V SV by LV SB 1 plus dou sigma by dou beta, okay. So all the parameter is positive only, right? So Cn beta is positive. So what you have said here, Cn beta positive, it is coming, okay, coming, right? So you can draw the graph also. This is one case and this is the another case. This is, let's say, first case, this is second case, beta, this is Cn. So which case will be the positive, which case will be the stable, which case unstable? First one, right? Stable, second one unstable, okay, and we have proved the same also, okay. You can put contribution coming from the vertical tail, and we have seen horizontal tail volume ratio, right? ST LT divided by SC bar, right? So similarly this you can write vertical tail volume ratio, this part you can write V into V. So okay, so your expression will be Cn beta equal to eta V VV 1 plus dou sigma by dou beta, okay. So this about the stability, okay. Now we'll talk about the directional control, okay. So we'll give the lecture name here, aircraft directional stability and control, okay. So the stability part is over. We will discuss now directional control, okay. Now elevator we have done in longitudinal case, aileron for the lateral case, and now last one is rudder. This is primary aerodynamic control surface, elevator, aileron and rudder. So rudder, okay. So if the rudder is deflected in this way, my thumb is pointing downward, right? So my deflection will be considered as a positive towards this direction. That means rudder is deflected in this direction, so it is positive, and in this direction negative, right? So if your yawing is happening in this direction, you have to deflect the rudder in opposite direction, this direction, to generate the vertical force in this direction and counter the same. So this one is a positive and this one is negative. Okay. Positive, negative, okay. Small n yawing moment minus L V into LV. This you can write half rho V square S B Cn, and this you can write half rho Vt square SV, and then lift coefficient that you can write in terms of vertical lift slope, and since you are deflecting the rudder, you will write tau into delta R, this into L. This we have already seen how to convert the lift coefficient in terms of contour surface deflection in lateral and longitudinal case as well. Okay. Now you can further write Cn is 1 half rho v square Vt divided by half rho v square is eta V, and SVLV divided by SB, which is vertical tail volume ratio, CL alpha of the vertical tail. Okay, and here you will write tau, and this is delta R. Okay, now differentiate with respect to delta R. Please note down this. Okay, I have written yawing moment half rho square SB into Cn. Cn is yawing moment coefficient, and then minus half rho Vt square SV. I have just expanded the LV, and then what is the lift coefficient coming? I have written in the control surface deflection in terms of control surface deflection, and then into LV divided by, I have divided half rho square, and then you can see half rho square Vt divided by half rho square eta V, and then SV LV divided by SB is VB, tau CL alpha of the vertical tail delta R. Fine. Now if you differentiate with respect to delta R, you will get Cn delta R, which is minus eta V VV tau CL alpha of the vertical tail. Okay. Are you aware of this? Cm delta E minus eta VH tau CL alpha of the tail. I already explained this, right? In longitudinal case, right? It is same only, right? It is same. Eta, eta, V, V. Volume ratio, volume ratio. Okay. See. Control derivative, control derivative. Tail efficiency factor, tail efficiency factor. Tail volume ratio, tail volume ratio. Tau, tau. Lift curve slope, lift curve slope. Only just in this case it is horizontal tail, and in this case it is vertical. So you can see exactly what doing. In horizontal tail, you can see horizontal tail and putting the support. You can think in that way, right? So expression is same, right? So what is the job of the directional control? First thing is, for example, like if you are rolling, okay, you are rolling the aircraft by increasing the lift here and decreasing the lift here, and if the lift is more here, the drag will be more here. If the lift is less here, drag will be less here. So that differential drag will try to yaw in this direction. But since you are rolling in this direction, so you don't want this motion, right? So what you will do? You will deflect the rudder in this direction to counter this yaw. That is how you will achieve the coordinated turn. Without side slipping, you are rolling the. That is the one job of rudder. What do you think can be the other job? Let's say commercial aircraft is flying, two engine, right? If one engine is failed, so what? Thrust is coming in this direction, right? So if this engine fails, this will try to take a yaw, right? So you have to counter that yaw. So you have to deflect the rudder in this direction to generate the force and counter the same, right? Okay. So in this case also, you are using the rudder at a asymmetric thrust condition. One engine fail or one engine is partially working, not producing the thrust as you want, less thrust. Then in that case you can use two best use I have told you, right? Your aircraft is stalled, so you are not producing any lift. So your altitude is losing, and at the same time you are yawing also, and that yaw rate is more than compared to the roll and pitch rate. That phenomena is known as a spin. So in this case, to stop the spin, you can use the rudder. Okay. So there is like many cases where the rudder is very important, and one more important case, for example, you are in a situation where the crosswind is coming and you want to land the aircraft. So in that case, okay, you can handle the side slip angle. For example, like in mathematically also you can see Cn is, you can write Cn beta into beta plus Cn delta r into delta r. So if you want to make no yawing moment, okay, so Cn delta r into delta r you can write, and delta r you can write minus Cn beta divided by Cn delta r, okay, into delta r. Beta, okay, this case simple. I don't want to, I will use rudder in a, to kill my yawing moment which is coming from the, let's say, side slip. Okay, now Cn beta is what, already positive, Cn delta is negative, so negative will be the positive. Okay, so if your side slip angle is what, side slip angle is sin inverse V by capital V. Okay, so let's say some your aircraft having velocity 30 meter per second and the crosswind 5 is coming. So can you tell me what is the angle? Sin inverse 5 divided by 30. Can you tell me the answer? What is the beta is coming? 9.59 degree, right? Your beta is coming, right? Let's say Cn beta is 0.01 and Cn delta r is also 0.01. Okay, so what will be the delta r? It will be this is minus sign. Okay, so this will be 1 into, let's say, beta. So beta, what is the beta is coming? 9.5, right? Okay, delta r. So delta r, how much is required? Approximately 10 degree. Positive, right? So positive, which direction? Which the direction is called positive? This direction is positive, right? Okay, this direction is positive. So if you deflect the rudder in this direction, what kind of motion will happen? This motion, right? This. Okay, so consider this scenario. What I have taken, wind is coming 5 meter per second, let's say crosswind 5 meter per second is coming, and direction is positive, right? Okay, so that means aircraft will try to take a yaw, it will try to have a side slip like this. So if you do the side slip like this and you are landing, then you will not touch at the landing center point, right? You will skid, right? But if you deflect the rudder in this direction, which is coming on 10 degree, you will counter the yaw and you can land your aircraft. Okay, so that is the importance of a rudder as a directional control. Okay, so this is all about the directional stability and directional control. Thank you very much.